Hi guys. Okay, today we're going to start chapter 8 with section 8.2, critical points and points of inflection. So you'll be introduced to the second derivative and what it does, to points of inflection and to concavity, which is concave up, concave down. It's just concave is the curvature of the graph. Concave up would be it would curve upward. Concave down would be curve downward. For example, if you have, let's say, a cubic, then concave down would be from negative infinity to this point right here. And concave up would be from that point in the middle, which is called the point of inflection. Point of inflection to positive infinity, that would be concave up, and this would be concave down. Okay, so take a look at the vocab here. Go ahead and write it down. You can pause the video and take the notes as you need. I'm just going to go through it here. A point where the derivative is 0 or undefined is called a critical point. So when you find the 0 of the derivative, or when it's undefined, that is called a critical point. Something critical is happening there. The y value of the critical point is a local max or local min. So we've talked about this before. For example, let's say you have a graph like this on the x and y axis. Let's just say there. Then the local max and local min would be what you typically would know as would be the hump. So this would be a local max, but the global max would be the highest y value of the graph, which is called global, or can also be called an absolute max. And that is typically when you're given a domain from, like, let's say 0 to a, then you have to find the global, which is what would be the absolute max from 0 to a, which is that endpoint there. Same thing goes with a local minimum. Local minimum would be your typical max and min. But when we're talking about global or absolute minimum, that would be the lowest point in the interval from 0 to a, global minimum or absolute minimum. Back in the days, they used to use global, but I think now it's more, they use absolute max and absolute minimum. Okay, so let's talk about what the second derivative does. The second derivative, which is the same exact way you were to take the derivative. Remember, we start off with our regular function, and then when you take the derivative of that, that would be f prime. Take the derivative of f prime, that would give you f double prime. That would be the second derivative. So what the second derivative tells you is concavity. If the second derivative is negative, which is what that first statement says here, f double prime of c less than 0, then the function in that interval is concave down. So it would kind of look like it would be facing down. If the second derivative is positive, that's the second statement here, then f of x would be concave up. And the point where it changes concavity, so like I showed you in the first slide, if you have a function like this, right in the middle, not necessarily, for this problem it would be in the middle, but right here where it changes concavity, where the second derivative equals 0, that's called a point of inflection. Point of inflection. Or we just abbreviate it PI. Okay? So on the next slide, let's talk about, or let's look at the sign analysis chart. So the first chart up here, we have the derivative. And remember, the derivative means slope. So where we have a positive sign, that means our graph is going up. Where we have a negative, that means our graph is going down. Same here. And right at these numbers, 1, 2, and 3, something's happening. These are critical points. So at 2, because it says infinity, that means it's undefined. But at 3, since it says 0, this is a 0. With our second chart, it's second, let me turn down the volume here. The second chart, it's second derivative. Second derivative means concavity. Concavity. Where you have a positive, that means your graph is going to have a concave up. Where you have a negative, it's going to be concave down. Again, at 2, it's undefined. At 3, it's a 0. And for the second derivative, 0 means point of inflection. But for the first derivative, at 3, a 0 for first derivative means a max, min, or plateau. If you look at the signs, it goes from a negative to a negative. That is a plateau because the signs do not change. So we're going to sketch a graph here according to these rules. EP stands for endpoint. So from 1, 2, and 3, I'm going to sketch a graph with all these characteristics. At 1, I have an endpoint, so it's just going to be a solid point. Now, the first derivative says it's increasing, and the second derivative is concave up. So I have to kind of make it curve upward, and it's increasing. At 2, it's undefined. And because the first derivative is undefined, the second derivative is automatically undefined. In order for a derivative to be undefined, you either have to have a vertical asymptote or a cusp. I'm going to draw a cusp right there at 2. Between 2 and 3, the first derivative is negative. That means it's decreasing, but it's concave up. So how would you draw a function that's going down but also concave up? Well, you can kind of curve it like that. You see how it has an upward curvature? That's still concave up, but your graph is going down. At 3, it's a plateau. So it needs to kind of flatten out. And then it keeps decreasing, and it's concave down. So you can kind of curve it down like that. So that would be a sketch of both of these characteristics with concavity and increasing and decreasing. Okay, so let's go ahead and do this problem here. We are going to find the first derivative. It says write the equations of the first derivative, second derivative, use them to find the local max, min, or plateau actually, and points of inflection. For local max and min, remember that that's the zeros of f prime. The points of inflection, that's the zeros of the second derivative. The first derivative is going to be negative 3x squared plus 8x plus 5. The second derivative will be negative 6x plus 8. Solving for the first derivative, solving for the first derivative will give me the max, min, or plateau. Now, because it's a quadratic, you can try different methods. You could try factoring, but factoring will not work. So I'm going to go straight into the quadratic formula. I get x equals to negative 8 plus or minus 8 squared, which is 64, minus minus 4 times negative 15, all over 2 times negative 3, which is negative 6. Again, anytime in this recording, you can stop, do the work, and make sure you got the same thing I did. Adding those two, the 60 and 64, I get positive 124 in the radical. The negative 8 and negative 6 become positive 8 plus or minus square root of 124 over 6. After you simplify and you add 8 plus square root of 124 divided by 6, I get negative 0.523, and subtracting 8 minus square root of 124 divided by 6, I get 3.189. Or vice versa. But when you separate 8 plus 8 minus square root of 124, these are the two values that we get. Okay? Now, if we graph this, this is a upside down parabola passing through negative 0.523 and 3.189. Those are my two zeros. So upside down parabola tells me that my minimum is at x equals to negative 0.523 and my max at 3.189. Looking at my signs here, because I go from a negative to a positive, negative 0.523 will be my minimum. And when I go from a positive to a negative, that's going to be my max. Okay? So take a look at the second derivative. The second derivative is when I solve the second derivative, which is negative 6x plus 8, find the zeros of negative 6x plus 8. That is going to give me the point of inflection. So subtract 8 to both sides, divide by negative 6, and I get x equals 4/3 after you reduce. Okay, this solution is what we call the point of inflection. Point of inflection. This point is where the curvature changes direction. When you graph this linear equation, here, it's a line. It's going to pass through the point 4/3 because that's a 0, so it crosses the x-axis. It's a negative slope of negative 6, so my line is going to go downhill. Oops, totally missed it, sorry. Right there. Okay. Now, from negative infinity to that 0, since the line is positive, that means, so from negative infinity to 4/3, parentheses on both, that means that my graph is concave up. I think I'm actually jumping to part B, where it's asking me for the intervals of increase in concavity. That's okay though. And from 4/3 to infinity, because it's below the x-axis, from 4/3 to infinity, it's concave down. So it acts the same as when you're describing intervals of increase and decrease, but now we're just talking about concavity.